let me draw a function that would be interesting to take a limit of. And I'll just draw it visually for now, and then we'll do some specific examples a little later. So that's my y-axis, and that's my x-axis. And let's say the function looks something like, I don't know, I'll make it a fairly straightforward function. Let's say it's a line for the most part. Let's say it looks just like that, except it has a hole at some point x is equal to a. So it's undefined there. And let me black that point out just so you can see that it's not defined there. And that point there is x is equal to a. This is the x-axis. This is the y is equal to f of x axis. Or let's just say that's the y-axis. And let's say that this is f of x, or this is y is equal to f of x. Now, we've done a bunch of videos on limits, and I think you have an intuition on this. If I were to say, what is the limit as x approaches a? And let's say that this point right here is L. We know from our previous videos that, well, first of all, I could write it down. Let's see, the limit as x approaches a of f of x. What this means intuitively is as we approach a from either side, right? As we approach it from that side, what does f of x approach, right? So when x is here, f of x is here, is right there. When x is here, f of x is there. And as we see that it's approaching this L right there, right? When you approach from that side. And then when we approach a from that side, right? And we've done limits where you approach from only the left or the right side, but to actually have a limit, it has to approach the same thing from the positive direction and the negative direction. But as you go from there, if you pick this x, then this is f of x. F of x is right there. If x gets here, then it goes here. And as we see, as we get closer and closer to a, f of x approaches this point L, right, or this value L. So we say that the limit of f of x as x approaches a is equal to L. And I think we have that intuition. But this was not a very, it's actually not rigorous at all in terms of being specific in terms of what we mean as a limit. You know, all I've said so far is as we get x gets closer, what does f of x get closer to? So, in this video, I'll attempt to explain to you a definition of a limit that has a little bit more, or actually a lot more, mathematical rigor than just saying, you know, as x gets closer to this value, what does f of x get closer to? And the way I think about it, it's kind of like a little game. The definition is, so if this means, this statement right here means that if you want to, that I can always give you a range about this point. I can always give you a range. And when I talk about range, I'm not talking about it in the whole domain range aspect. I'm just talking about a range like a, you know, as long as I'm no further than, I can give you a distance from A. As long as I'm no further than that, I can guarantee you that f of x is not going to be any further than a given distance from L. And the way I think about it is, it could be viewed as a little game. Let's say you say, okay, Sal, I don't believe you. I want to see, you know, whether f of x can get within 0.5 of L, right? So let's say you give me 0.5. You give me 0.5, and you say, Sal, I want, you know, by this definition, you should always be able to give me a range around A that'll get me that'll get f of x within 0.5 of L, right? So the values of f of x are always going to be right in this range right there. And as long as I'm in that range around A, as long as I'm the range around you give me, f of x will always be at least that close to our limit point. F of x will always be at least that close. And let me draw it a little bit bigger, just because I think I'm just overwriting the same diagram over and over again. So let's say that this is f of x. This is the whole point, right? And there doesn't have to be a hole there. The limit could equal actually a value of the function, but the limit's more interesting when the function isn't defined there, but the limit is. So this point right here, that is, let me draw the axes again. Let me draw, so that's x-axis, y-axis, x, y. This is the limit point L. This is the point A. So the definition of the limit, and I'll get back to this in a second because now that it's bigger, I want to explain it again. It says this this means, and this is the epsilon delta definition of limits, and we'll touch on epsilon and delta in a second, is I can guarantee you that f of x will, you give me any distance from L you want, right? And actually, let's call that epsilon, and let's just hit on the definition right from the get-go. So you say, I want to be no more than epsilon away from L. And epsilon can just be any number greater, any real number greater than 0. So that would be, this distance right here is epsilon. This distance there is epsilon, right? And for any epsilon you give me, any real number, so this is, you know, this would be L plus epsilon right here. This would be L minus epsilon right here. The epsilon delta definition of this says that no matter what epsilon you give me, I can always specify a distance around A, and I'll call that delta. I can always specify a distance around A. So let's say this is delta less than A, and this is delta more than A. This is the letter delta. And this is delta more than A. Where as long as you pick an x that's within A plus delta and A minus delta, as long as the x is within here, I can guarantee you that the f of x, the corresponding f of x, is going to be within your range. And if you think about it, this makes sense, right? It's essentially saying, I can get you as close as you want to this limit point just by, you know, and when I say as close as you want, you define what you want by giving me an epsilon. It's a little bit of a game. And I can get you as close as you want to that limit point by giving you a range around the point that x is approaching. And as long as you pick an x value that's within this range around A, as long as you pick an x value around there, I can guarantee you that f of x will be within the range you specify. And so, you know, just to make this a little bit more concrete, you could give me, let's say you say, I want f of x to be within 0.5. Let's just, for, you know, make everything concrete numbers. Let's say this is the number 2, and this is, let's say this is number 1, right? So we're saying that the limit as x approaches 1 of f of x, I haven't defined f of x, but it looks like a line with a hole right there, is equal to 2. This means that you could give me any number. Let's say you want to try it out for a couple of examples. Let's say you say, I want f of x to be within let me do a different color. I want f of x to be within 0.5 of 2, right? So this would, you know, I want f of x to be between 2.5 and 1.5. Then I could say, okay, as long as you pick an x that's within, I don't know, I could, you know, it could be arbitrarily close, but as long as you pick an x that's, let's say it works for this function, that's between, I don't know, 0.9 and 1.1, right? So in this case, the delta from our limit point is only 0.1. As long as you pick an x that's within 0.1 of this point, or 1, I can guarantee you that your f of x is going to lie in that range. And so hopefully you get a little bit of sense of that. Let me define that with the actual epsilons delta, and this is what you'll actually see in your math textbook. And then we'll do a couple of examples. And just to be clear, that was just a specific example. You gave me one epsilon, and I gave you a delta that worked. But in order for this, by definition, the definition of the epsilon, if this is true, or if someone writes this, they're saying it doesn't just work for one specific instance. It works for any number you give me. You can say, I want to be within 1/millionth of a, you know, 1 to the or 10 to the negative 100th power of 2, you know, super close to 2, and I can always give you a range around this point where, as long as you pick an x in that range, f of x will always be within this range that you specify, within that, you know, 1/trillionth of a unit away from the limit point. And of course, and the one thing I can't guarantee you is what happens when x is equal to a. I'm just saying you can get, as long as you pick an x that's within my range but not on a, it'll work. Your f of x will show up to be within the range you specify. And just to make the math clear, because I've been speaking only in words so far, and this is what you see in the textbook. It says, look, you give me any epsilon, so give me any epsilon greater than 0. And anyway, this is a definition, right? If someone writes this, they mean that you can give them any epsilon greater than 0, and then they'll give you a delta. They'll give a delta, right? And remember, your epsilon is how close you want f of x to be to your limit point, right? It's a range around f of x. They'll give you a delta, which is a range around a, right? Let me write this. So limit as x approaches a of f of x is equal to L. So they'll give you a delta, where as long as x is no more than delta of, so as long as, so the distance between x and a, right? So if we pick an x here, let me do another color. If we pick an x here, the distance between that value and a, as long as, one, that's greater than 0, so that x doesn't show up on top of a, right? Because the function might be undefined at that point. But as long as the distance between x and a is greater than 0 and less than this x range that they gave you, it's less than delta. So as long as you take an x, if I were to zoom the x-axis right here, this is a, and so this would right here would be, this distance right here would be delta, and this distance right here would be delta. As long as you pick an x value that falls here, so as long as you pick that x value, or this x value, or this x value, as long as you pick one of those x values, I can guarantee you that the distance between your function and the limit point, so the distance between, when you take one of these x values and you evaluate f of x at that point, that the distance between that f of x and the limit point is going to be less than the number you gave them, right? And if you think of it, it's almost, it seems very complicated, and I have mixed feelings about where this is included in most calculus curriculums. It's included in like the third week before you even learn derivatives, and it's kind of this very mathy and rigorous thing to think about, and it tends to derail a lot of students, and a lot of people I don't think get a lot of the intuition behind it. But this is it is mathematically rigorous, and I think it is very valuable once you actually study more advanced calculus or become a math major. But with that said, this does make a lot of sense intuitively, right? Because before we were talking about, look, I can get you as close as x approaches this value, f of x is going to, as x approaches this value, f of x is going to approach this value. And the way we mathematically define it is, you say, Sal, I want to be super close. I want the distance to be f of x and L, I want it to be 0.00001. Then I can always give you a distance around x where this will be true. And I'm all out of time in this video. In the next video, I'll do some examples where I prove the limits, where I prove some limit statements using this definition. And hopefully, when we use some tangible numbers, this definition will make a little bit more sense. See you in the next video.